This video is going to talk about some of the key issues around multicollinearity. There are three cases that we're doing in class, so the new food case, the quality control case, and the HMO case. And it's really essential that you work through those cases either before watching this video or after, or probably both. Okay, so let's talk about the effects of omitting a relevant predictor. So suppose that we estimated a model that had only x1 in it. So we just have, in the case of new food, we only regress sales on advertising. So advertising would be this x1 variable. But the real model is a function of more than that one variable. It's really a function of two variables. So if you think about new food, we have x1 as advertising, but we know that store volume is also affecting sales, and we really need to have that in the model. So if you go back to the new food solution, there's not a direct analog, but think of model 3 where we had advertising in it, and we estimated the effective advertising is 20.5 as being analogous to this misspecified model, the first one, where we only had one of the two predictors that we really need in there. And then the part 3C, where we included volume, is analogous to the second model, where we control for this relevant predictor. All right, if x1 and x2 are correlated, so in the case of new food, advertising and volume were found to be correlated. So let's go back to the solution. That the correlation between volume and advertising is a minus 0.74. Okay, so we have two predictor variables, advertising and volume, that are correlated. And whenever this is the case, B1 estimated from this first model is going to be biased. Now, the direction of this bias is going to depend on two things. So it's going to depend on the correlation between x1 and x2 and the sign of the volume effect. So let's go trace this through. The correlation between advertising and volume is negative, so minus 0.74, and the volume effect was positive. So recall that, let's go back to the solution, the larger the store, the more you would sell of new food. So that volume coefficient, that's B2, is positive. Okay, this table is indicating that we're going to have a downward bias, and sure enough, that's exactly what we observed. So let's go back to the previous model. We observed that the effect of advertising was 20.5. This theorem that I've just shown you is going to say that this result is going to be downwardly biased. And sure enough, once we control for the effect of a volume, the advertising effect shoots up to 131, which is going to be more the real effect. So once we hold volume constant after controlling for volume, the true effect of advertising is 131. So this is a really difficult issue in model building, because you never know when you're going to have one of these omitted predictor variables. In the case of new food, Pillsbury found out the hard way that they had this omitted variable, and only after they'd made a really bad decision on advertising. So these omitted predictors that are correlated with other variables are examples of multicollinearity. So what is multicollinearity? Well, multicollinearity is when your x variables are correlated with each other. So y has nothing to do with this. It's just correlations between the x's. And the problem with this multicollinearity is that we cannot sort out individual effects. So the effects of the x's are going to be confounded. They're going to be tangled up with one another, and we're not going to be able to sort them out. And so what we'll see are a number of effects. So we'll get unstable coefficients where they'll have high standard errors, plus when we add or drop coefficients, the magnitude changes wildly. So we certainly saw this with new food where the coefficient went from 20.5 to 131.3. And so what's happening there is that uh, you know the advertising effect, when it's in there alone, is attempting to do some of the explaining that volume should be doing. And once you bring volume in, then advertising uh, assumes more of what it should be showing. So we're going to see these various effects through all three cases that we do on multicollinearity. So new food, quality control, and the HMO case. Now, one interesting feature is that predicted values are not affected by multicollinearity unless you extrapolate. So let me give you an example of this. Suppose that the true model is exactly this. So y is 2 times x1 plus x2. There are no errors. So this is an unusual situation where we don't observe any error, which is great, right? Now I've generated 3 observations from this model. So let's take the value x1 equal to 1, x2 equal to 2. So if we plug that in, 2 times 1 plus 2 is 4, is my y value. Likewise with the other two. Now you'll note that there's a bit of a problem because x2 is perfectly correlated with x1. All right, so the x2 value is always twice that of the x1 value. Now I've plotted this in R, and so you'll see it over here. I've got a little matrix X, and if I correlate the two columns of X, you're going to see, sure enough, the correlation between the first two columns is 1, and all the points fall in this line. All right, well, the first model, the true model, of course, fits perfectly because that's what generated the data. However, all of these other models also fit perfectly. So if we were to take this first model, well, we could take 4 times x1, and you'll notice that 4 times 1 is 4, 4 times 2 is 8, 4 times 3 is 12, plus 0x2. That fits perfectly as well. Likewise, if we were to take no x1 plus 2 copies of x2, okay, so 2 times 2 is 4 and so forth, we also get perfect estimates, so an R squared of 1. Finally, we could take 6 copies of x1 and subtract 1 copy of x2 and also get perfect fitted values. Now, the point I'm trying to make with this very simple example is that my conclusions change completely depending on which of these models I choose, and they all give me perfect estimates. So in this first case, I would conclude, x1 is a very powerful predictor, x2 has no effect. If I were to get these estimates, I would say, well, x2 is a very important predictor, x1 has no effect. And if I chose this third model, I would say, well, x1 is a very important positive predictor, while x2 has a negative effect. And you'll see that all of these substantive conclusions are completely wrong in that, the way I rigged the data was that both of these were going to have some effect. So which one is correct? The answer is we can't tell from these data. The reason we can't tell is because of the confounding that we have between x1 and x2. Now, I mentioned earlier that predicted values are unaffected unless you try to extrapolate. Okay, so what do we mean by extrapolation? What I mean by extrapolation is if we were to wander off this subspace, so the subspace being the line defined by, x2 equal to 2x1. So if I were to wander off either direction from this line, the predicted values would be way off. So let's take a simple point that doesn't fit on that line. Let's take x1 equal to 1 and x2 equal to 1. So clearly the correct answer is 2 plus 1, which is 3. But you'll note that all of these other models get it wrong. So extrapolation is going to be especially questionable when you have multicollinear data. How do we detect multicollinearity? There are a couple ways. The The simplest way, and one way that you should always practice, is to examine the correlation matrix. So large correlations are going to indicate that multicollinearity could be a problem. However, there are other ways that we could do this. So there's quite a few measures that are available in software. Two other measures that I find pretty useful are tolerance and the variance inflation factor, otherwise known as VIF. Now, let me explain where tolerance comes from and VIF. So tolerance is going to be 1 minus the r squared value from a regression of, x1 on all the other x's. Let's go back to new food for a second, and I'll illustrate exactly what I'm talking about with this. So we've got the new food data set, and let's say I wanted to study the amount of multicollinearity in this data set. So of course the correlation matrix tells us something about that, but let's examine how much multicollinearity there is with volume. Okay, so I'm going to fit a new linear model. Let's call this fit 2, and we'll do an LM. This time I'm going to say volume is the dependent variable. And the other variables that I've had in my model were price plus advertising plus location. Now, if I do a summary on fit 2, you'll see that I can, my r squared is about 0.584. So I can explain 58% of volume if I knew price, advertising, and location. Now you'll see that price and location don't really contribute, they're not significant, but ad sure does. Okay, so the tolerance value is going to be 1 minus 0.584. So this is the tolerance value for volume. To get to the variance inflation factor, what I'm going to do is take 1 over this. So if I take 1 over that value, I'm going to get 2.4. Now let's go back and estimate the original model. So sales equals price plus ad plus location plus volume. And if I do a VIF on fit, what you'll see is that the variance inflation factor for volume is 2.40, and that's exactly what I found doing it the hard way, doing it by hand, if you will. So returning to the course packet, what you'll see is that if you have no multicollinearity, then that variable, so if a variable has no multicollinearity, you're not going to be able to predict it from the other variables in the model. All right. In that case, the r squared will be about 0, and tolerance will be about 1. So if you take 1 over something that's about 1, you're going to get about 1. So values of the variance inflation factors of around 1 mean no multicollinearity. The extent to which these values become large indicates that you have multicollinearity. And so if we go look at this, location, recall, was not located to much of anything. VIF is around 1, indicating there is no problem. Price wasn't really related to anything, and sure enough, the VIF is around 1. Advertising and volume had fairly large values. So that's just a nice diagnostic that you have to help you understand where you have multicollinearity. I forgot to mention one thing. You need the CAR package, CAR, which you can download from the, you can install it from the CRAN website. What do you do if you have multicollinearity? Well, the answer to that question somewhat depends on what you're using the regression model for. So remember that I said that there's really 2 main uses of regression. We either use it to make an accurate prediction. So I'm trying to forecast the dependent variable. I don't really care about the relationships with the independent variables. The other possible use of a regression is more of an interpretive use, where you're trying to understand how individual x's affect the y. So if all you care about is predictions, then multicollinearity is not such a big deal, as we saw in that little example, because we'll still get very good predictions. So you could potentially do nothing, although there's a lot of work in data mining that attempts to improve on this with various methods like ridge regression, the lasso, principal components regression, and others. And sometimes you get a bit of improvement doing these methods, but it's not a big issue, not a giant issue the way it is when it comes to interpreting them. Now, when it comes, if your goal in building the model is to interpret the regression coefficients, you've got a substantially bigger issue on your hands. So the best advice that I can give you is to avoid multicollinearity if you possibly can. And the way you do that is with an orthogonal design. So we saw that with New Food. Had they switched two of the cities so that one of the cities with the high advertising budget had small stores, and another city with high advertising got high volume had we need all combinations of high volume, low volume, high advertising, low advertising. So if they'd switched it, they would have had a much more orthogonal design, and we wouldn't have run into the problems that we ran into. Often that's not the case. It's just not going to be an option to gather more data. In that case, what you really need to do is to understand why you have multicollinearity. And if you have an understanding of why you have it, that'll give you some hints on what you should do about it. So here are some reasons why predictor variables may be correlated. So one is that you've got the wrong model. So x1 is really a cause of x2. We saw that in the case of quality control, where the rate of production was determining the temperature variability. So if this is the situation you're in, the remedy is pretty obvious. You should fit the correct model. So regress defects on rate, for example, or regress all the pieces in that chain. So defects on density on temperature variation on rate. So that's one solution. Let's take a look at the last one. So the last one is really the New Food situation where you've had bad luck. So if you've had bad luck, as we had, where by bad luck, two of the cities that had the smaller stores happened to get assigned to the city, to the high advertising condition, and the largest stores got assigned to the low advertising condition. What you're going to do in that case is include controls. So we bring volume into the model. You can use one of these shrinkage estimation methods that, like principal components regression, ridge regression, but the main thing is including the controls. The third situation is what we see with the HMO case, where our predictor variables are really manifestations of some common underlying latent variable. And this one's going to be substantially more difficult, and it may just be impossible to sort out the individual effects. So that's it for this introduction to multicollinearity.